These are the corrections for the Chapter 2 test in pre-calculus. In problem 1, you were asked to say which term or terms describe this system. We use elimination to solve this system for x by multiplying 2 times the bottom equation and adding it to the top equation. We get 11x equals 11, and therefore x equals 1. This alone is enough to say that the system is consistent and independent, since there's nothing in either system that would cause y to be undefined. Therefore, C is the best answer. In problem 2, you were asked to determine which system of equations corresponds to the graph. Notice that the lines intersect at the point 2, 2. Therefore, we only need to try 2, 2 in each equation to find which system is correct. In A, 2 plus 2 is equal to 4, and 3 times 2 plus 2 is equal to 8. Therefore, A is the best answer. To solve this algebraically, we can see that simply adding them won't work. However, if we multiply the top equation by 2 and add the result to the bottom equation, the result is 13x equals negative 5. And therefore, x equals negative 5 over 13. We can find y by substituting that into the first equation and solving for y. Remember, when you're multiplying a fraction and an integer, you can make the integer a fraction by putting it over 1 and then multiplying the numerators and the denominators. Continuing to solve gives us another problem involving fractions. This time, since we're adding, the fraction that we make negative 3 must be over 13. To get the numerator, we multiply negative 3 times 13 to get negative 39. Now we can add the numerators and put the result over the denominator of 13. Multiplying both sides by a negative 1 changes their signs, and y equals 1913. Therefore, the point negative 5/13 and 19/13 is the answer. In solving this matrix problem, we set up the matrices to show our work. Then we subtract corresponding elements to get the answers. In solving this matrix problem, we show that we're multiplying the matrix by 3 by writing 3 next to our matrix. We then multiply each element of our matrix by 3. This matrix problem is testing your knowledge of equality of matrices. When two matrices are equal, their corresponding elements are also equal. Therefore, we have two equations. 5 equals negative 4x, and negative 3x equals 5y. Solving the first equation for x gives us negative 5/4. We can substitute this value into the other equation to solve for y. Again, we're multiplying a fraction and an integer, so we make the integer a fraction by putting it over 1 and multiply the numerators and the denominators. Now, instead of dividing by 5, we will multiply by the reciprocal of 5, which is 1/5. This time, before we multiply the numerators and the denominators, we can cancel a 5 out of each of those. The result is y equals 3/4. The bars on the outside of this matrix mean find the determinant. To find the determinant, we're going to multiply negative 3 by negative 7 and subtract 5 times 2. The result is 21 minus 10, or 11. To find the inverse of this matrix, we must first find its determinant. We follow the same procedure as in problem 7, multiply negative 3 times 1, and subtract 7 times 5. This result gives us negative 38. Since the determinant is not 0, this matrix has an inverse. To find it, we change the places of 1 and negative 3 and change the sign of 5 and 7. Finally, we multiply the whole matrix by 1 over the determinant. The result is the inverse matrix. To solve this system, we will use matrix equations. We'll put the coefficients of the matrix in this 2 by 2, and we'll put the numbers on the right-hand side of the equation in this 2 by 1. We will enter the 2 by 2 into the calculator as A, and the 2 by 1 as B. We can then multiply the inverse of A times B and convert into fractions to get x equal to 4/5 and y equal to 2/5. Therefore, A is the best answer. To solve this system, we will enter this into an augmented matrix, which will be 3 by 2, or 2 by 3. In the left-hand 2 by 2, we will enter the coefficients of the x's and y's. And in the right-hand 2 by 1, we will enter the numbers on the right-hand side of the equations. Entering this into the calculator and using RREF, then converting to fractions, gives us this matrix. This indicates that the system is consistent and dependent and therefore has infinitely many solutions. As in 10, we will turn this system into an augmented matrix. This time it will be 3 by 4. However, the second equation is not ready to be entered into the augmented matrix. We must get the 1 on the other side by adding 1 to both sides. The result is y plus z equals 1. Since there's no x, the entry in the second row, first column, will be 0. Entering the rest of the system into the matrix gives us 2, negative 1, 1, negative 3 across the top, then 0, 1, 1, 1 in the middle, and 1, 1, negative 1, and 9 on the bottom. Entering that matrix into the calculator and using our REF again, we get the answer as 2, 4, negative 3. To graph this system, we know that we will be working in the first quadrant due to the first 2 constraints. The last constraint has a y-intercept of 2 and an x-intercept of 6. To figure out which side to shade, we will use a point. 0, 0 is usually a good one. And test it in the inequality to see if it works. In this case, 0 is less than or equal to 6, and therefore we shade that side. This result tells us that C is the correct answer. We can graph the inequalities here to find the vertices. First, we solve the third one for x, or for y, giving us y is less than or equal to 4 minus x. Then by graphing on the calculator, we get the feasible region shown. We get the vertices 4, 0, 1, 0, and 1, 3. Since the optimization equation is simply adding the coordinates of the points, we get a maximum of 4 and a minimum of 1. Therefore, D is the correct answer.